So this is Islaris, a piece of tooling we've been working on for reasoning about machine code with respect to realistic architecture semantics. So firstly, why do we want to reason about machine code? And there are two main reasons. The biggest one is, at the end of the day, your machine code is what actually gets executed on hardware. If you do a verification in some higher level language, before it runs, you have to either trust or verify some compilation process. And this is either a big gap in your proof or really, really hard. Whereas if you verify your machine code, you're kind of done. The other thing is we do see some code that gets written in assembly still because it has to be. The main example of this that we think about is exception handlers in operating systems and hypervisors. These tend to be written in assembly because they interact with low-level systems features that aren't exposed by higher-level languages. And they're also really important because they protect user space and kernel space from one another. And so getting it right is important, and we want to verify them. Okay, so we want to verify machine code. What's the challenge here? Why can't we just do this like super straightforwardly? Write down our instruction semantics, plug it into whatever our favorite verification framework is, and we're just done. And the problem is this first step, write down the instruction semantics, that can be quite involved. Mainly because for reasons of scale, the ARM architecture reference manual is 11,000 pages or so long. And I really, really don't want to be the person who has to transcribe that into Coq. So ideally, we would do verification of machine code, but with respect to some pre-existing mechanization of the semantics. And we're kind of in luck here, because there do exist mechanizations of at least some ISA semantics already. These are, sorry, the ones that we use are primarily provided by the Sail project. So Sail comes with a number of different semantics for different architectures. The ones that we're the most interested in are those for ARM v8 and RISC-V. There's kind of two reasons why we hear the most about these, which is that the semantics we have are complete and authoritative. By complete, I mean that the Sail semantics for ARM and RISC-V cover the complete sequential architecture behavior. And by authoritative, I'm talking about the fact that the RISC-V Sail spec is a part of the specification for the RISC-V architecture published by the RISC-V Foundation as part of their golden model. The ARM v8 Sail spec is compiled automatically from the ASL specification published by ARM. Okay, so we want to do verification with respect to the Sail semantics. The problem now is that they're still really large. Like the Sail semantics for ARM v8 are like 125,000 lines of code. If you compile this to Coq, it gets worse by something like a factor of 2. And we've tried doing this, and you feed this into Coq, and it just melts down, and you run out of memory, and you can't prove anything. You might be wondering, sort of, where does all this complexity come from? Like, you think about some simple instruction you might want to reason about, like this one, which adds 64 to the stack pointer. Surely this is very simple, right? We just take the register containing the stack pointer and increment it by 64. If you go and look at the specification, this is a small fragment of it. There's a whole bunch more going on here than you might expect. So firstly, addition is co-specified with subtraction, because if you specified all of the instructions separately, the spec would be 10 times longer than it already is. You also have to deal with flag setting, because arithmetic instructions can optionally set condition variable flags for use in branches. The third line there is figuring out the operand. And you'll notice if it's the stack pointer, that's not just a register, that's a banked family of registers that you need to pick between based on the exception level. The exception level is ARMism for like what mode is the processor executing in, user mode, kernel mode, etc. That's not, you'll notice there's not even any arithmetic happening on this slide. That's in another function, which is doing a bunch more arithmetic than it needs to because it's also computing all of those flags. And I haven't even gotten to decode, which is like a medium complex size and complexity parser hidden inside of the spec that you also need to reason about. And that's for like one of the simplest instructions you can think about that isn't a no-op for doing some arithmetic. As soon as you want to touch virtual memory, or memory at all, life gets a million times harder. So I'll hand over now to Michael to talk about what we've done to try and deal with all of this complexity.
Yes, thanks, Angus. So our key insight in Islaris for dealing with this large ISA models is to realize that they can be separated into two parts. One can first observe that large parts of the ISA specification are in fact irrelevant for a given instruction and system configuration. So the first step of Islaris is actually to prune these irrelevant parts of the large ISA models. For this, we use and extend the ILA framework, which can eliminate unreachable code paths in these ISA models. In particular, Isla uses SMT-based symbolic execution to condense this large ISA model to a small description of the relevant aspects for a given instruction and system configuration. SMT solvers are a good fit for this task because they can deal with this large ISA models and efficiently generate these descriptions of the relevant aspects. So with these descriptions in hand, we can now turn to the actual task of the actual verification of code against these relevant parts of the model. And here we get all the usual challenges of verification of assembly level languages. So we want to have modular reasoning principles for reasoning about registers, memory, or also count pointers, which are very common in assembly-like languages. For this task, we build a program logic using Iris. So you might have heard of Iris in the previous 2 talks in the session already, but very briefly, Iris is a separation logic framework in COG, which has been applied to many different languages before, and we use it to build a program logic for reasoning about these descriptions of the relevant aspects of the ISA models. In particular, this gives us a nice semi-automatic verification tool in COG where we get nice modular reasoning principles from Iris, which we then can combine with automatic and manual proof as necessary. So altogether, we take Isla's SMT-based symbolic execution together with the nice modular reasoning principles from our Iris-based program logic to obtain Islaris. So now let's have a look how all of these parts actually fit together. What does a user need to do to verify their code using Islaris? First, the user takes the instruction that they care about and the constraints on the system state and feeds them to the Islaris frontend. The Islaris frontend that passes that on to Isla, which uses an SMT solver to generate an Isla trace, which is this simplified description of the relevant parts of the ISA model. The Islaris frontend then generates a deep embedding of this trace in COG, where the user can also write down a specification and use the Islaris program logic and proof automation together with manual proofs to verify the instructions against the specification. So this is the overall workflow of using Islaris. Now I want to go into more detail about the 2 parts of Isla and the Iris-based program logic. Let's start by looking more into Isla. Here you can see the Isla trace for the add instruction, which Angus just showed us, with the constraint that it's executing at the exception level 2, so a hypervisor level. Particularly, you can see here that this trace first reads the stack pointer, then it adds 64 to it, and then writes back the updated value to the stack pointer register. But maybe more important what's here is what's not here. And for example, you can see there's no flex computation because this variant of the add instruction actually does not update the flex register, so Isla removes this for us. Also, this decode function, which Angus showed at the very end, is simplified away by Isla. And maybe most interestingly, you can see here that this Isla trace directly uses the SPEL2 register. So this means Isla figured out for us that this is the right version of the stack pointer register to use, given the constraint that we're executing at exception level 2. So this is already very nice to have the simplified description of the model at hand, but how can we now take this and build a verification of a larger program out of this? And this is where the Iris-based program logic comes in. And I want to highlight 2 aspects of this program logic. First, it gives us nice modular reasoning principles thanks to being a separation logic. And here I just want to quickly explain this, this rule for verifying a write rec micro instruction, which was part of this Isla trace. So here we can say we have the precondition that the register R points to the value v prime before the write rec. And thus, after we apply the rule, we know afterwards the register R contains the value v. But implicitly, through the use of separation logic, this tells us that the write rec also does not modify any other register. So we can get nice modular reasoning here. But of course, using rules like this by hand can become very tedious for larger, more complex instructions and larger programs. This is why we also built proof automation for this separation logic. In particular, so here you can see actually the verification of the example I will show in a moment. And just want to highlight here we have this LIA run tactic, which automatically discharges the separation logic reasoning for this example, and it generates some pure side condition about bit vectors, which is solved by this BV solve tactic here in the end. Of course, not all proofs have this level of automation. Sometimes for more complex specification, you need some manual proof, but that integrates well with this form of proof automation. And I also quickly want to mention that this proof automation is based on Lithium, which comes from the Refined C project, which is a foundational and automated verification tool for C, which was presented last year at PLDI, and I'll be giving a reprise of the talk later today. So if you're interested, we can talk about that there. So now we've seen these two parts of Islaris. We've seen Isla and the Iris-based program logic, but what interesting stuff can we do with this? So here I want to just briefly show you an interesting example that we verified using Islaris. So this is some code which sets up, first installs an exception vector, and then calls that exception vector. So, and there's a lot of interaction with the architecture state happening in this example. So first, this code writes to some system registers to set up the exception vector. And then it performs an ERED instruction, which does a lot of things, but the main thing it does is it switches the exception level, so the privilege level, from exception level 2 to exception level 1. So you go from the hypervisor level to the operating system level. Then we directly do an hypercall back to the exception level 2, back to the hypervisor, where we then execute the exception vector, which we have set up before, which just writes 42 to x0 in this example, and then returns back to exception level 1. So here, like the specification here is that kind of at the end, x0 contains 42, but of course, verifying the specification involves making sure that all these switches of the exception level and all of these interactions with the system state work correctly. And yes, so this example shows that actually Islaris can actually verify such low-level code which interacts a lot with this architecture state and manipulates it. Of course, this is not the only example that we've verified in Islaris. In fact, there are quite a few more case studies. Briefly want to highlight. We have also verified an exception handler from Google's PKVM hypervisor. We've also verified interesting code which uses function pointers. So we've verified a binary search implementation compiled from C, which uses a function pointer for the comparison. And there are many more things in the paper. So like a formal definition of the semantics of this Isla trace language, where we saw the traces before, description of like the Islaris program logic and the proof automation. And of course, so what we've done here, most of it is not specific to ARM, but also applies to RISC-V. And for RISC-V, we actually also did have a translation validation result where you can take whether you can actually check that the output of Isla matches the semantics of when you take the RISC-V sale model and directly translate that into COG. And yeah, for ARM, this doesn't really work because the ARM model is just too large. So yeah, and there are more things in the paper, but with that, I just want to briefly summarize that Islaris enables verification of machine code against these authoritative ISA models, and it does that by combining this ILA-based, SMT-based symbolic execution with an Iris-based program logic. And with that, we would like to thank you for your attention, and we're looking forward to your questions.
Am I understanding right from your big system diagram near the beginning that everything before an arrow goes into the dashed boundary that says calc is trusted in this tool setup?
In the normal use case, yes. So you're in the, let's go back to the, right. Yes, so usually like we didn't verify an SMT solver, and like Isla is also trusted. So there's this one thing which I briefly mentioned at the end, which is kind of this translation validation, where you can then also take the sale model of RISC-V and directly translate that into COG, and then prove that the Isla traces or that it refines kind of the Euler traces which Euler produces, and then you can kind of compose the proofs such that you only trust like the Coq model generated from Sale, and yes, for the verification.
Is that automatic translation validation, and how expensive in time is it?
It's semi-automatic translation validation, so it's not fully automatic. Like we have some tactics which kind of automate large parts of it, but and it's like the main thing is that kind of Coq becomes slow once you work with kind of these larger instruction models. So it takes some time, and we're hoping, for example, for future work that having maybe a better Coq generation from the Sale code would make this a lot easier, and also maybe make this translation validation more feasible for maybe for ARM. But yeah, we haven't done that yet for this work, but we're hoping to maybe have something like that for future work.
Thank you.
Is the generated Euler code always guaranteed to completely remove all unnecessary information, or does it just pare down the amount of unnecessary reasoning you might need to do?
So no, it's not guaranteed to remove everything. There's a couple of reasons for that. One is it depends on the quality of the SMT solver. So it's possible to have some branch that's unreachable, but Z3 can't prove that it's unreachable, and then match neutral by default if Euler fails or just produces the uncertain branch, but it has to do one of the two. And I guess the other thing is you can imagine like behavior that you don't care about, but which does happen, and Euler doesn't remove that. It's only pruning like actual execution branches. But if the SMT solver can see that the branch won't happen, then it doesn't appear in the trace. That's sort of the guarantee that you get.
Cool. Thank you.
So one thing I wondered about, because you talked about traces, what happens when I have a loop?
Then you have a buggy architecture.
Well, I mean, I write a program that has a loop, but I don't know how often it runs. So how does that look like as a trace?
So the traces are traces of like single instruction architecture behavior. So the kind of the traces that we showed an example of, that was the trace for just an add instruction, right? And if the add instruction has an unbounded loop inside of it, then your architecture is broken and you should complain to ARM. If your program has a loop inside of it, that's fine. Handle it the normal way you would a program logic. You get in a program that bounces between several bits of execution, and you have to reason about the PC to reason about what is executing at any given time. But that's
so when
fine.
You say trace, you only mean trace within a single instruction.
Yes, when we trace means trace within an instruction.
Okay, well, let's thank the speakers again.